This is the second part of the Chapter 9 problem session on equilibrium chemistry. And in this part, we're going to focus on equilibrium chemistry involving acids and bases. So there are several relationships that you need to know. You need to know that Kw is equal to the concentration of hydronium times the concentration of hydroxide, and that is equal to 1.0 times 10 to the negative 14 at 25 degrees C. This is the most important equilibrium constant that you will have. Now notice what this says. If I know the concentration of hydronium, I know this value, I can calculate the concentration of hydroxide. If I know the concentration of hydroxide, I just divide 1 times 10 to the negative 14 times the concentration of hydroxide, and that gives me hydronium. Okay, so that's the first relationship that we need. The next relationship that you need is that pH is defined as negative log of the concentration of the hydronium cation. pH is negative log of the hydronium cation. And pOH is defined as negative log, and this is a base 10 log, of the concentration of hydroxide. And then one other thing that will help you solve these problems will be to know that pH plus pOH is equal to 14. So these relationships will enable you to quickly determine every one of the values on this table. So here's what you need to know. If you know any one of these values, the concentration, remember the square brackets stand for concentration in moles per liter. If you know the concentration of hydronium, then you can determine the concentration of hydroxide, the pH, and the pOH. Okay, so if you know hydroxide, you can calculate hydronium, pH, and pOH. If you know pH, you can calculate hydronium, hydroxide, and pOH. If you know pOH, you can calculate any of the other three. So you need to be able to do that. So let's start with the first row. If the concentration of hydronium is 3.8 times 10 to the negative 18, then we're going to use this relationship here, which is that whenever you multiply the concentration of hydronium times the concentration of hydroxide, you always get 1 times 10 to the negative 14. So the concentration of hydroxide is going to be 1 times 10 to the negative 14 divided by the hydronium ion concentration, 3.8 times 10 to the negative 8. Okay? And that calculates out to be 2.6 times 10 to the negative 7. 2.6 times 10 to the negative 7. That's the concentration of hydroxide when the concentration of hydronium is 3.8 times 10 to the negative 8. The product of this number and this number is 10 to the negative 14. Okay. Now to get pH, we just take the base 10 logarithm of the concentration of hydronium. The log of 3.8 times 10 to the negative 8 is equal to 7.42. That's the pH. The pH is equal to 7.42. The pOH of this. Now, the easiest way, once we have pH, the easiest way to get pOH is to realize, and this comes from the definition of pH, the product of the concentrations is 10 to the negative 14. So pH adds up to pOH to get 14. So to get pOH, it's going to be 14 minus 7.42. And that's going to be 6.58. That's the value you'll get there. So let me highlight the answer, and this shows you how you did each one of the questions. So these are relationships you need to know for this exam. Okay, in the next row, if the concentration of hydroxide is 7.6 times 10 to the negative 2, what is the concentration of hydronium? Well, just remember that the concentration of hydronium times the concentration of hydroxide is always equal to 10 to the negative 14. So that means that the hydronium ion concentration, I know hydroxide, I'm going to divide both sides by the hydroxide ion concentration. It's 1 times 10 to the negative 14 divided by the concentration of hydroxide, 7.6, times 10 to the negative 2. And when you calculate that out, you will get that the hydronium ion concentration is 1.3 times 10 to the negative 13. 1.3 times 10 to the negative 13. Okay. That's the hydronium ion concentration. Now, I just want to show you, if you started with hydroxide, the easiest way to get pH, if you started with hydroxide, is to first get POH. Think of the lowercase p as just taking the base 10 logarithm and changing the sign. So this is the definition of POH and pH. pH is negative log of the concentration of hydronium ion, and POH is negative log of the concentration of hydroxide ion. So we're going to take the concentration of hydroxide, which we know, and POH is negative log. By the way, I should have included this negative sign back here. I took the negative log of this. It changed the sign so that pH became positive. Be sure and fix that. So I have the negative log of the concentration of hydroxide, 7.6 times 10 to the negative 2. And when I do that, the POH is 1.12. 1.12. Now, once you know the POH, the easiest way to get the pH is to subtract POH from 14. pH is 14 minus POH, 1.12. pH plus POH, this is the third relationship you need to know. pH plus POH, they always add up to 14. So 14 minus POH equals the pH. The pH is 12.88. Now let's look at these numbers briefly so that you can see what's going on. So this is the hydronium ion concentration and the hydroxide ion concentration. Okay. In this particular case, 10 to the negative 2 is a much bigger number than 10 to the negative 13. There's a lot more hydroxide, so this is a basic solution. Notice that the pH is 12. Any pH greater than 7 is basic. The POH is very small. If the POH is small, if it's less than 7, it's basic. Okay, let's do the next one. The pH is 3.75. The easiest thing to do then is to get POH. It's going to be 14 minus 3.75, so the pH will be 10.25. POH is 10.25. This is an acidic solution. If pH is less than 7, it's acidic. There's more hydronium ion. Now, if pH is equal to negative log of hydronium, if I knew the concentration of hydronium, I could calculate pH this way. How would I go from pH back to the concentration of hydronium? And you do it this way. The concentration of hydronium is equal to 10 to the negative pH. So 10 to the negative 3.75. If I know pH, I can get the hydronium ion concentration. 10 to the negative 3.75 is 1.8 times 10 to the negative 4. That's the concentration of hydronium ion. And now to get the concentration of hydroxide, you can also use, this is just the inverse of the first two relationships that I highlighted here. The concentration of hydroxide is equal to 10 to the negative POH. So I know what POH is. It's 10.25. 10 to the negative 10.25 calculates out to the concentration of hydroxide, which is 5.6 times 10 to the negative 11. Now look at these numbers. If pH is 3.75, that's acidic. If pH is less than 7, it's acidic. And that means there's more hydronium, 10 to the negative 4, than hydroxide, 10 to the negative 11. An acidic solution has more hydronium than hydroxide. Okay, there's one more. Now, given any of these values, you need to be able to calculate the others. If POH is 5.55, the first thing I'm going to do is calculate pH. 14 minus 5.55 will give me the pH, because pH plus POH always equals 14. And subtract those, I get 8.45. 8.45. So if the POH is 5.55, the pH is 8.45. Now to get the hydronium ion concentration, we saw that if we know the pH, we raise 10 as a power to negative pH to get the hydronium ion concentration. Here's the pH, so 10 to the negative 8.45 calculates out to be 3.5 times 10 to the negative 9. 3.5 times 10 to the negative 9. And if I know the POH, I can calculate the hydroxide ion concentration. 10 to the negative POH, negative 5.55, will give me hydroxide ion concentration. You plug that into your calculator, you get 2.8 times 10 to the negative 6. Now look at these numbers. You'll see that there's less hydronium. 10 to the negative 9 is a smaller number than 10 to the negative 6. More hydroxide, less hydronium. So this is a basic solution, and that's confirmed. The pH is greater than 7. If the pH is greater than 7, it's basic. So this pH is greater than 7. This is slightly basic. This is very basic. The pH is much greater than 7. This is acidic. The pH is less than 7. This is basic. The pH is greater than 7. Okay, the next question says, what is the pH of 0.055 nitric acid? Now, what you have to know here is that nitric acid, HNO3, is a strong acid. Nitric acid is a strong acid. And that means that when you put HNO3 in water, it completely breaks up to form H plus aqueous plus NO3 minus aqueous. So if you start with 0.055 moles per liter of HNO3, it will completely break up all of it to give 0.055 molar hydrogen ion and 0.055 molar nitrate. Now remember that when we say H plus means exactly the same thing in aqueous solution as hydronium. H plus aqueous is exactly equivalent to H3O plus aqueous. That is, the concentration of H plus aqueous is exactly equal to the concentration of hydronium. Now this is a strong acid. It completely dissociates, and so to get the pH here, pH is equal to negative log of the concentration of hydronium. And this is a strong acid, so pH is equal to negative log of 0.055. Hydronium means exactly the same as H plus, and so when we calculate pH, pH calculates out to be 1.26. That's a low pH. That shouldn't surprise us. This is a strong acid. It's a fairly concentrated strong acid, and that's pH. There are 7 strong acids and that you need to know, and there are 7 strong bases that you need to know. So nitric acid is a strong acid. Sodium hydroxide, NaOH, is a strong base. It's a strong base. And that means that when you put sodium hydroxide in water, it completely dissociates into sodium cation. There's a one-way arrow. It breaks up to form sodium cation plus hydroxide anion. Okay. So that if you start with 0.028 moles per liter of sodium hydroxide, it will completely break up. You won't have any of this left, and you'll have 0.028 moles per liter sodium cation and 0.028 moles per liter hydroxide. So in this case, we know, therefore, that the concentration of hydroxide is 0.028 moles per liter. Now, if you know the concentration of hydroxide, can you get the pH? Notice how many of these questions start, what is the pH of? What is the pH of? What is the pH of? This says, what is the pH of? And this one gives us the pH. But you're going to get a lot of questions that ask you to determine what is the pH of. And the easiest way to do this, if I know the concentration of hydronium, let's calculate the pOH. So in this case, pOH is equal to negative base 10 log of the concentration of hydroxide. Okay. pOH is equal to negative log of 0.028. And when we calculate that out, the pOH calculates out to be 1.55. So that's what the pOH is. Well, how do I get pH? pH plus pOH equals 14. So if I know pOH, I can get pH. pH equals 14 minus 1.55. That calculates out to be 12.4 0.45. Now, that is a high pH. That means it's a basic solution, and that shouldn't surprise us because sodium hydroxide is a strong base. So the pH is 12.45. The next question, what is the pH of 0.028 molar strontium hydroxide? Now, you need to know that, first of all, you need to know that SrOH2 is a strong base, and that it has two hydroxides, has two OH minuses. That's very important. You have to take those into account. Now, the other strong bases that have two OH minuses are calcium hydroxide and barium hydroxide are also strong bases with two hydroxides. They are also strong bases with two hydroxides. So you have to know that. So that means that when you dissolve strontium hydroxide in water, strontium hydroxide, since there are two hydroxides, and it's a strong base means there's a one-way arrow. It completely breaks up to give strontium 2 plus aqueous plus 2 OH minus aqueous. Okay. And so if I start with a concentration of strontium hydroxide of 0.028, I need another 0.028 moles per liter, then when it breaks up, the concentration of strontium would be 0.028 moles per liter. But for every 1 mole of strontium hydroxide, I get 2 moles of hydroxide. That's going to be 2 times 0.028, or 0.056 moles per liter. Don't forget that there are 2 of those that it completely breaks up, and we'll have that much, 0.056. So now that we have that, let me draw a line to distinguish from the previous problem. And POH is equal to negative log of the concentration of hydroxide. This is the concentration of hydroxide, 0.056. It's the base 10 log. When you take that logarithm for strontium hydroxide, you get 1.25. POH equals 1.25. pH equals 14 minus 1.25, so the pH calculates out to be 12.75. That shouldn't surprise us. This is a strong base. It has a high pH. So if you have either a strong acid that we saw on this question up here, or a strong base as we saw here, it's a one-way arrow. You do not solve it like an equilibrium problem. The concentration of the strong acid is the same as the concentration of hydrogen ion, which is the same as hydronium. We just hit the log button and that gives us pH. The concentration of a strong base, if there's one OH, it's the same as the concentration of hydroxide. We hit the log button, we get POH, and we subtract that from 14 to get the pH. If it's either strontium hydroxide, calcium hydroxide, or barium hydroxide, we have to take into account you get twice as much hydroxide per mole of strontium, barium, or calcium hydroxide. And that's the concentration of hydroxide. We get the POH. We subtract that from 14 to get the pH. But what if you have a weak acid? A weak acid, such as acetic acid, you're given the Ka for this weak acid. You're given the Ka. Now, the shorthand for writing any weak acid is we can say HA stands for a weak acid. And that reacts with water. I'll put aqueous. That reacts with water. If it's a weak acid, it reacts with water in an equilibrium. It's not a one-way arrow. It's an equilibrium to form A minus aqueous plus, and an acid is a proton donor. It's going to donate this H plus to hydronium. So when it donates the H plus to water, rather, it will form the hydronium cation, H3O plus aqueous. This is an equilibrium. When all else fails, if you have an equilibrium, set up the ICE table, the initial change equilibrium. The initial amount of weak acid is 2.75 times 10 to the negative 2. 2.75 times 10 to the negative 2. We always leave the liquid out. We don't do any calculations with the liquid. Over here, initially, this is 0, and initially, this is approximately 0. In pure neutral water, it's actually 10 to the negative 7, but that's so small we can ignore it. Now, the change is going to be, it's got to go forward because I don't have any of this, minus x plus x plus x. Now, what we can do with these weak acids, look at the magnitude of Ka. The magnitude of Ka, I'll highlight it, is 10 to the negative 5. 10 to the negative 5 is so small that x is extremely small compared to this number, and we can ignore it. X is extremely small compared to this number, and we can ignore it. So on the equilibrium line, 2.75 times 10 to the minus 2 minus x. X is so small right here that we can ignore that. That's 2.75 times 10 to the negative 2. We can ignore that x. I can't ignore this x. 0 plus x is x. And here, hydronium, this is so small, I can ignore this. This is about x. So we set up the ICE table. We ignored this because Ka is so small that x is very small compared to this. Now, we will plug these values in to the Ka equation. If all else fails, set up the ICE table, and then plug the equilibrium values into the Kc equation. Let me draw a line here to distinguish it from the previous problem. And here's what Ka looks like. Ka is an equilibrium constant for an acid. It's just like every other equilibrium constant. We'll take products over reactants. We leave water out. Remember, in a heterogeneous equilibrium, you omit the solid or liquid. So it's going to be in the numerator, A minus times the concentration of hydronium divided by the concentration of HA. And that's equal to 1.8 times 10 to the negative 5. Okay. So let's plug in these equilibrium values. So in the numerator, I'm going to have x squared, because x times x is x squared, divided by 2.75 times 10 to the negative 2. Let's take this out so it's not in scientific notation. Let's call this 0.0275. That way that we won't get confused, that's not an x. So divided by 0.0275 equals 1.8 times 10 to the negative 5. We solve for x. We cross multiply, we take the square root, and when you solve for x, x calculates out to be 7.03 times 10 to the negative 4. Now at this point in an acid-base problem, when I set up the Ka equation, I always ask, what does x represent? And when I go back to this table, x represents the equilibrium concentration of the conjugate base of acetic acid, and x represents the equilibrium concentration of hydronium. This is the concentration of the hydronium cation. And that means that all I have to do to get the pH is to hit the log button. The pH is equal to negative log of 7.03 times 10 to the negative 4. Okay, so when I hit the log button and I change the sign, then my pH calculates out to be 3.15. The pH is 3.15. This is an acidic solution. Now notice it's not as acidic as the previous problem we did with the strong acid. The strong acid, there was a lot more H+. It had a much lower pH. It was more acidic. But this is acidic, a 3.15 pH. Okay, let's look at the last problem using acid-base equilibria. Okay, for this last problem, the key to solving this problem is, now we're given the concentration of the acid and we're given the pH. The key to solving this problem is anytime you know the pH, you can easily determine the equilibrium concentration of hydronium. Because pH is just a different way of saying the equilibrium concentration of hydronium. Hydronium ion concentration at equilibrium is equal to 10 to the negative pH. That's equal to 10 in this problem to the negative 3.42. And when you calculate that 10 to the negative 3.42 is 3.8 times 10 to the negative 4. That's the hydronium ion concentration. That's the pH. Okay, so I have a weak acid. Let's set up the ICE table. The ICE table looks like this. HA is the shorthand that we use for any weak. And this says monoprotic. Monoprotic means there's just one proton here. HA is the shorthand we use for any weak monoprotic acid. If it's a weak acid, then we show this weak acid reacting with water in an equilibrium. This is an acid. It donates its proton to water. That means it donates its H plus to water. That leaves A minus aqueous plus hydronium, H3O plus aqueous. We set up the ICE table, so initial, change, equilibrium. The concentration of the acid is 0.18. That's the initial concentration, 0.18 moles per liter. We always leave water out of these equilibrium equations. The initial concentration of A minus before this reacts is 0. The initial concentration of hydronium before this reacts is approximately 0. It's really a 10 to the negative 7, but that's approximately 0. This is going to go forward, so we put minus X plus X plus X. Now, I don't know what Ka is, so I don't know if I can ignore X or not. So I'll put 0.18 minus X, X, and X. So that's the ICE table. When all else fails in an equilibrium problem, you set up the ICE table. Well, the next thing that you will do is plug these equilibrium values into the KEQ equation. Now, I do need to point this out, that I know what X is because I know the equilibrium concentration of hydronium. X is 3.8 times 10 to the negative 4. That's what X is, because I know the concentration of hydronium. The key to solving this is anytime you know the pH, then you also know the concentration of hydronium ion. So let's plug this into the Ka equation. Ka equals, and it's always products over reactants raise their coefficients. So X times X, so it's going to be X squared in the numerator, divided by 0.18 minus X. So, or Ka equals, well, I know what X is. It's the concentration of hydronium. So in the numerator, 3.8 times 10 to the negative 4, and that whole value squared, divided by 0.18 minus 3.8 times 10 to the negative 4. I'm just going to let my calculator do all of this. And when I do and I solve for Ka, and I'm only going to have two significant figures because of the way that we calculated this, then I get Ka is equal to 8.0 times 10 to the negative 7.